Welcome back. In the last session, we had seen classroom workbook problems and we solved till problem number 11. Now let's start some concept. Therefore, let me cover some concept, then we'll see the problems. Okay. Okay. Tell me, what did we see till now? We have seen amplifier. When I say amplifier, it could be inverting amplifier, non-inverting amplifier, voltage to current converter, log amplifier, sine wave to square wave conversion. Therefore, we have seen all these things, right? And then few more, some signal processing in terms of DC signals. Now, let's see something called some other processor, or I can say integrator and differentiator. Okay, just write integrator. Okay, just listen. What do you mean by integrator? What is integrator? Integrator is a circuit which integrates, right? Yes, integrator is a circuit which integrates the input signal and then give you output, which is integration of your input. I agree, right? Now, maybe if you want to design an integrator, first of all we should know what is an integrator and what is the mathematical equation of integration of any input. And if you know that, and there are two ways to analyze anything like frequency domain analysis and time domain analysis. First of all, let me go ahead with frequency domain analysis and then let's get the requirement which circuit satisfies the integration, and in time domain the same thing I'll explain, and then let's see which circuit satisfies the integration even in time domain, which is easier. Remember, to get the answer, frequency domain analysis is always easier, and to understand in a better way with respect to time domain analysis is always useful to understand. But remember, both are useful, both qualitative analysis, quantitative analysis. I can say frequency domain analysis is kind of quantitative analysis and time domain analysis is kind of qualitative analysis. We will understand what's happening or what will happen inside the circuit with respect to the input signals. Now, let's see what is an integrator requirement. Then tell me, when I say this is what is my integrator, black box for me, but I'm just representing with a symbol integrator, and let me say this is what is your V naught of t and this is VI of t. Therefore, I'm giving signal at the input. I'm expecting my output V naught of t is equal to integration of VI of t. Therefore, let me say V naught of t is equal to integration of VI of t dt. Right? Now I'm trying to find the transfer function of the system, and which system satisfies the transfer function what we get from this, that can be used as an integrator. I hope this is clear, right? I'm not taking any circuit. I'm just taking it as a black box and expecting what is my output. To get this output with respect to the input, I'm trying to find the transfer function. Then the circuit which satisfies the transfer function, that will act as an integrator, right? That is what. Therefore, tell me, if I convert into S domain, VA of t, then you will have VA of S. Then V naught of t, you will have V naught of S. Tell me what is V naught of S. If VA of t is VA of S, then what is integration of VA of t dt in S domain? That is nothing but what? VA of S divided by S. 1 by S into VA of S from Laplace equations. Now tell me what is transfer function. Therefore, transfer function H of S is equal to V naught of S divided by VA of S. Right? Therefore, what is V naught of S? V naught of S is nothing but 1 by S into VA of S divided by VA of S. Then it is left with what? 1 by S. Then if you convert into S, omega, S is equal to J omega, then you will get what? 1 by J omega. Then if I take only magnitude, not phase, then mod h of j omega, mod h of j omega is equal to 1 by omega. This is what is our magnitude response. Let me convert into dB. If I convert into dB, then mod h of j omega into dB is equal to 20 log 1 by omega, right? Therefore, now if I plot the frequency response, then we will get the answer, right? What is the frequency response? Therefore, if you take frequency response, let us say this is what is omega, and let me start with 1. When I start with 1, therefore maybe what is log 1 by a minus log a? Therefore minus 20 log omega, right? Therefore now if you ask me, x-axis is omega, y-axis is mod h of j omega in dB. Okay. Therefore now tell me, when omega is 1, then log 1 0. Therefore this is 0 dB. When omega is equal to 10 and minus 20, and then if you do, you will get something like this. Therefore, let me start with 0 dB here. This is 0 dB. Then this is what is 10. Now this is 100, etc. Therefore now if you do, this is minus 20 dB. And if you do, because 20 log 100 is nothing but 10 square. 2 into 20, 40. Log 10, 1. Therefore minus 40, etc. Therefore, if you see here, the system which is having frequency response having a slope minus 20 dB per decade, that can be used as an integrator. That is what it is saying. Therefore, this is what is having the slope minus 20 dB per decade. This is having slope minus 20 dB per decade. The system which is having the slope minus 20 dB per decade, that can be used as an integrator. Therefore, the frequency response or magnitude response should fall with respect to the frequency with the slope minus 20 dB per decade. If you have that system, that can be used as an integrator. Therefore, tell me which circuit satisfies the relation, the frequency response relation. Which circuit is having something like this? Can I say low pass filter? If you consider low pass filter, right, then wherever we have frequency response having a slope minus 20 dB per decade, in that portion we can use that low pass filter as an integrator. Can I say that? It should have a slope minus 20 dB per decade. Not only that, if you consider band pass filter, there also you have slope minus 20 dB per decade. Even if you consider band pass filter, wherever in plot frequency range the slope of the function or system is minus 20 dB per decade, then that also can be used as an integrator. Very simple. In frequency domain, wherever you have the gain decrease with respect to frequency with a slope 20 dB per minus 20 dB per decade, that can be used as an integrator. I hope this is clear. Okay. You take it, then we will consider low pass filter, then we will see, right? Maybe let me complete, therefore I will give you the time to write down. Therefore, now the question is, let us consider low pass filter. Let us consider low pass filter. If you consider low pass filter, what is that? Simply RC circuit. This is your V0 and this is what your Vi, right? What is transfer function? H of S is equal to 1 by SC, voltage division network, divided by 1 by SC plus R, right? 1 by SC plus R. Therefore, tell me if I take SC, LCM, that will be cancelled, then you will get 1 by 1 plus SCR, right? Then if you substitute S is equal J omega, then you get S is equal J omega, H of J omega is equal to 1 by 1 plus J into omega into R into C. Therefore, what is omega? If you write down 1 by 1 plus J into 2 pi F into R into C, right? Can I write it as like this? This is nothing but 1 by 1 plus J into, right, F divided by 1 by 2 pi RC. I can write like this, right? Therefore, this is what people call it as, therefore H of J omega, H of J omega is equal to 1 divided by 1 plus J into F divided by 1 by 2 pi RC. In this case, it is called as FH, higher cutoff frequency, where FH is nothing but, where FH is 1 by 2 pi RC. Okay. Therefore, now tell me, what is mod H of J omega? Mod H of J omega is equal to 1 by 1 plus F divided by FH whole square root. This is what is your magnitude. And if you convert into dB, you will get it. Okay. Anyway, let me plot. Then what you get if I plot Bode plot? Okay. This is what your frequency, F or omega, anything is fine. Okay. Therefore, now this is what is mod H of J omega. Let me convert into dB. If you convert into dB, okay. At lower frequencies, right, when the frequency, right, is less than FH, then you can say it is almost 0, then it is almost 1. Then if you do Bode plot, we have a pole at 1 by RC, right, minus 1 by RC, left of the S plane, but here it is positive. Therefore, till that you will not see anything. Then I can say, if you plot Bode plot, this is what is our higher cutoff frequency, FH 1 by 2 pi RC. Wherever you see a pole, from that point onwards, you see this is what is 0 dB. Actually, this is your 0 dB, because F is equal to 0, let us say, then 1, 20 log 1, 0. Therefore, FH is equal 1 by 2 pi RC. Now, strictly, this is what is Bode plot. Bode plot means till you see a pole, the gain is flat. Whenever you see a pole, the gain will decrease with a slope of minus 20 dB per decade, right? But strictly speaking, this is for easiness, because if you want to draw the transfer function, if you want to draw a magnitude response from the transfer function, then find the poles zeros. Wherever you have a pole, till that the frequency response is flat. Then whenever you see a pole, then the frequency response will be decreasing with a slope 20 dB per decade. Okay. Therefore, now tell me, if you see actual plot will have, the gain will have the variation, but it will have curve like this. Then if you ask me, right, this is what is our real plot. Okay. Now if you ask me, this is what is our minus 3 dB point or half power point, or if you ask me at F is equal to FH, at F is equal to FH 1 plus 1 by root 2. What is 1 by root 2? Minus 3 dB, right? 20 log 1 by root 2 minus 3 dB. Therefore, that is what is minus 3 dB point or half power point, whatever may be. But according to Bode plot, we will not take the actual magnitude response with respect to frequency. To make it simple and easy, people take up to, this Bode plot explained that up to a pole you can take it as almost flat. After a pole you can say that is what is decreasing with a slope of minus 20 dB per decade. Anything, but both are drawn. The black one is with respect to Bode plot, red one is real frequency response with respect to your frequency. Okay. Now, what it may be, this is what is having a slope minus 20 dB per decade. Whether it is Bode plot or actual plot, it is having a slope minus 20 dB per decade, but it is not having slope minus 20 dB per decade for all the frequencies. But actually, according to the concept, integrated concept, The circuit which is having the slope minus 20 dB per decade, that is what is an integrator, which we can use it as an integrator. But here, in this frequency range only we have the slope minus 20 dB per decade. Wherever you have minus 20 dB per decade, in that frequency range only we will get integration. Therefore, what is the answer? Therefore, your low pass filter is nothing but integrator. Your low pass filter is integrator only if the frequency of your input signal should be greater than fh. Not slightly, at least 10 times, because here it is not minus 20 dB per decade. According to Bode plot, immediately we have minus 20 dB per decade, but actual scenario, practical considerations, then it is having minus 20 dB per decade after maybe I can say 10 times of fh if you take, there only you have slope minus 20 dB per decade. Okay, this is what is the condition or requirement. Therefore, what is f? The frequency of the input signal with which you are exciting the circuit, and fh, the higher cutoff frequency of your low pass filter, that depends on R and C, 1 by 2 pi RC. Okay, therefore we got to know that we can use low pass filter as an integrator only when f is very much greater than fh. The same thing I want to derive using time domain analysis, right? We didn't know, right? When I give a sine wave, integration of sine wave. When I give a square wave, integration of square wave. When I give step signal, integration of step signal. Without that, we got to know that RC circuit can be used as an integrator provided the frequency of the input signal should be very much greater than 1 by 2 pi RC. We got the answer. When can we use it as an integrator? But we don't know exactly what's happening with respect to time domain. Let me explain the same thing in a different way using time domain. Therefore, we will understand clearly. Then we will see the condition in the case of time domain, and let's compare whether we are getting the same condition or similar condition in the case of time domain or not. Okay, take this. After that, I'll explain using time domain analysis. I'll give you 2.5 minutes. Try to complete in 2.5 minutes. Therefore, this portion we can use as low pass filter. This is graphical representation, but the same thing is explained in sentence format. Okay, 30 more seconds. What is low pass filter? It passes low frequency signals, then after some frequency, then it is what is attenuating the signal. Okay, attenuating significantly, but till higher cutoff frequency, the attenuation will be 50% of the maximum output signal it can pass with respect to power. If you speak with respect to voltage domain, what is minus 3 dB 1 by root 2, which is nothing but 0.707. Means, let us say we are getting a signal some 1 volt peak to peak. I am giving 1 volt peak to peak sine wave. I am getting 1 volt peak to peak sine wave at very low frequency. That is nothing but passing as it is, because this is passive low pass filter, not active low pass filter. Okay. Now, I am keeping my input 1 volt peak to peak constant. I am keeping 1 volt peak to peak constant. but I'm changing the input signal frequency. 10 hertz, 100 Hz, 1 kHz, 10 kHz, 100 kHz. Therefore, I'm changing my input signal frequency without changing the input peak to peak. But if you see output signal peak to peak, whatever signal you are giving at the input, the same frequency component is expected at the output. Okay, just a minute. Just for your understanding, therefore, if you apply a sine wave, let us say this is what is 1 volt peak to peak, but having different input signal frequency Fi, then what is expected? I am expecting almost the same 1 volt peak to peak, but therefore as the input signal frequency is increasing, the output signal peak to peak is decreasing up to what? Let us say 0.707, means 70.7% of your input signal, if it is coming to the output, people are saying that it is acceptable and then passing the input signal to output. But once the input signal is not passed to your output signal more than 0.707, or if it is less than 0.707, as the output signal strength is decreasing, then people are saying that it is not accepted as the input, as input is passed to the output. Okay, if you ask me with respect to power, why it is only 0.707 or 1 by root 2, that has come from the power. If you see, when I give 1 volt peak to peak, I am getting the same, let us say I am getting the same signal 1 volt peak to peak. What is the power? Whatever power you are giving at the input, the same amount of power you are getting at the output. Therefore, whatever maximum output power you can get, that we are getting at low frequency. If you treat it as our reference power, which is 100%, let us say, then as your input signal frequency is increasing, then your output signal peak to peak is decreasing, your output signal power is decreasing, whatever power which you are trying to deliver to your load, that power is decreasing. Therefore, up to what power people agree that it is acceptable? That is nothing but 50%. Means the maximum power what you can deliver to the load, let us say at low frequency 100%, but as the signal frequency is increasing at the input, that 100% will become 80%, 70%, 60%, 50%, up to 50%. Therefore, the power which is what is delivered to the load is decreasing, decreasing, decreasing up to this point, which is nothing but minus 3 dB, which is nothing but 3 dB point or half power point. Till that point, the power what you are trying to deliver to the load is more than or equal to 50%. Once you cross that frequency, which is nothing but higher cutoff frequency, the power what you are trying to deliver to the load is less than 50%. People say that it is not acceptable. Therefore, the bandwidth, 3 dB bandwidth is defined as the maximum power what you can transfer to the load. If you take it as P0, 50% of that maximum power is okay. Less than 50% of maximum power what you can deliver to the load, if it is that, it is not accepted as signal is passed. Okay, it has something, some signal is there, but the gain is not considered as constant or not flat. But till this point, gain is considered as flat and it is acceptable. Okay, this is what is 3 dB bandwidth. If you ask me absolute bandwidth is nothing but in what frequency range your gain is flat, 99.9% flat. But then if you consider that, you see the frequency range is very less, then if you see low pass filter, that is not having, I can say, absolute bandwidth. That's why people define for all the systems typically 3 dB bandwidth. Okay, it deals with the power. 50% of maximum power is acceptable, less than 50% of maximum power is not acceptable. That is the reference people took, and then less than that frequency range is acceptable, more than that frequency range is not acceptable for low pass filter. Okay, now let's see the same thing using time domain. Okay, You have to remember this condition, okay? To get integration, the frequency of your input signal should be greater than 1 by 2 pi RC. Now, you take time domain analysis, therefore time domain analysis. Don't write, just listen here. Okay. Now, if you consider low pass filter or RC circuit, this is R, this is C, and this is what is V naught of T, and this is VA of T. Okay. Let us apply a square wave at the input. Therefore, this is what is the input. Okay. This is what is continued. This is your VA of T. Let us say having a time period T. This is 0, this is T by 2, and this is what is T. Okay. Now, if you apply square wave as input, let's see what is your output. Okay. Now, for that, let me take three conditions. Number one, the time constant of the circuit. What is time constant of the circuit? R into C. Okay. Now, I can say case 1 RC is very much less than the time T by 2. Okay. Therefore, you can say what I do, I'm explaining qualitatively, not quantitatively, and you know all those equations, what is voltage across the capacitor, V final plus V initial minus V final into e to the power of minus T by tau, right? If you do mathematically also you'll get it, but let me explain qualitatively, but that qualitative explanation is enough to see for what condition it can be used as an integrator. Okay. Now don't write. Therefore, let me plot what is output. When I give square wave, what is my output? Okay. I'll use three colors, but when you draw, you try to explain in that way. Okay. Now let us say this is what is my input. This is what is our input. Okay. Just 2 cycles are enough. Now, if you see, we want to plot V naught of T, V naught of T. Okay. Now, listen, case 1. Case 1. What is case 1? Your RC, the time constant RC, right, is very much less than T by 2. What does it mean? What does it mean? Your capacitor is charging very quickly within a time of T by 2. Right? Now, let's see. A step signal is given. Let us say 0 to some voltage V. This is what is going to some voltage V, and this is what is minus V. Okay. Therefore, now tell me. This is V and this is what is minus V. Now, tell me. Input is changing suddenly from 0 to V. Right? Voltage across the capacitor cannot be changed instantaneously, provided infinite amount of current can be passed through the capacitor. But practically we cannot pass infinite amount of current through the capacitor. Because we cannot pass infinite amount of current through the capacitor, voltage across the capacitor cannot be changed instantaneously. Then there is sudden change in the voltage, input voltage, but the output voltage will be 0. Therefore, let us say this is what is 0. Okay. Now tell me, but what it may be, within a time of T by 2, your capacitor is able to charge, because what is time constant? The time constant is very much less than T by 2. It can charge faster, or I can say it can charge in a time of T by 2. Then that is charging, therefore your capacitor charges. When that is what is charging, let us say this is what your output. It will not charge immediately, but it will charge to the voltage what you apply. And similarly, input is changing from plus V to minus V. Voltage across the capacitor cannot be changed instantaneously. Then that voltage will be dropped across the resistor. Then your capacitor slowly trying to charge to minus V. It is trying to charge within a time. Therefore, let us say this is what is trying to charge Now again input is changing from minus V to plus V. Then again it is also trying to charge and it is trying to again discharge. Okay, this is what is your output. Therefore tell me, maybe before that, what is integration of square wave? What is integration of square wave? Integration of square wave is triangular wave, right? Is it triangular wave? Triangular wave is nothing but linearly increased voltage, linearly decreased voltage, linearly increased voltage, linearly decreased voltage. It is increasing but not linearly. It is increasing exponentially because voltage across the capacitor changes exponential way, non-linear way. This is not linear way. Then can you say that it is an integrator? No, this is not an integrator, right? Now let's see, maybe I can take case 2. Case 2 is nothing but, I am using the same color coding. Let us say RC is equal to T by 2. RC is equal to T by 2, right? In this time, maybe I can say 67% of final value it will reach. Then if you ask me how it charges, now RC is not very small, but now RC is equal to T by 2. What is time constant? At time T is equal to tau, what is that? 0.67 times the final value it will reach. Okay, therefore 0.67 times of means like this. Therefore it will try to charge to final value, but your input is changed. Similarly, if I ask me your output will be 63% of final value. This is what you are going to get it. Now can you call this as a square wave? I can say the slope is little bit improved. Here completely non-linear, but little bit it is linear. But okay, this is also not completely called as a square wave. Now case 3. Case 3, RC value is very much greater than T by 2. Means, what does it mean? The time constant of the circuit is very much greater than T by 2. Means, in a given time of T by 2, your capacitor cannot charge. It will charge, but it will charge very slowly. We need to have more time. We need to have more time to see capacitor voltage reaches to V. What does it mean? Now your capacitor charges very slowly and reaches your final value V after a long time, but by the time we are changing your input from plus V to minus V, we are not waiting for capacitor to charge till V, right? But that is what is advantage. Let's see. Then if RC is very much greater than T by 2, in a time of T by 2, if RC is your capacitor is not charging, then how it charges? It charges very slowly. When it charges very slowly, it is like charging exponentially, but it is taking huge time. Okay, but whatever may be, in the meantime your input is changed from plus V to minus V. Then your capacitor is trying to charge to what? From this point, this is what is initial voltage to the capacitor at this point. Then it is trying to charge to what? It is trying to charge to minus V. If you leave for a long time, then it will reach to minus V, but we are not leaving, we are changing our input. Therefore let us say it is charging very slowly. Very slowly means it is what is going to non-linearly, but but your input is changing suddenly. Here also it will take huge time to charge. Then this is what it is. Is it a linear increment? Is it a linear increment? Yes, almost linear increment. Maybe if you ask me, I will explain. If you take voltage across the capacitor, when you give a step signal, the voltage across the capacitor, that is what is increasing exponentially. But if you see at the lower voltages, remember at the lower voltages, if you zoom this portion, okay, this is kind of linear. If you zoom this portion, this is kind of linear. Even though this is what is non-linear completely, if you take 0 to 5 times of time constant, which is like 5 into RC, then if you take less than or time t is equal to about 0, then in this portion it charges very kind of linearly, therefore you can take it as linear. That is what is basically, we are trying to make RC circuit very slow. When you are trying to make RC circuit very slow, what does it mean? Then your capacitor charges very slowly. When capacitor is charging very slowly, Remember, that is almost linear. It takes huge time to charge, means we are almost at this portion, that it is considered as a linear charge. Okay, approximately, not completely, but in that time. Therefore, it is nothing but linear. Therefore, can I say this is nothing but square wave, and we are getting triangular wave. Therefore, when you give square wave as input, we are getting triangular wave at the output. But the limitation of the circuit is your input square wave peak to peak is 2V, but output signal triangular wave is not 2V, because this is passive integrator. That's why we need active integrator. Not only doing integration action, we want amplification also. If you see the red signal, the peak to peak of our red signal is less than the peak to peak of your input signal. We want amplification also. It should be more than your input signal peak to peak. Let us say, then only I will call it as integrator, active integrator. That is what we will achieve using Opamp. Okay, but how to get that active integration, that part I will explain after this using virtual concept or what not maybe. But now in time domain, therefore what is this? This is what your integrator. Then if you ask me the conditions, therefore this is nothing but your RC what? Less than T by 2, and this is what is, you can say RC is very much greater than T by 2. This is what we need. Okay. Therefore, just write, wait, I will give you time. Therefore, tell me your low pass filter, RC circuit, your low pass filter, the low pass filter will be acting as an integrator. It is acting as an integrator only if, tell me the condition, only if RC is very much greater than T by 2. Right? Therefore, now tell me, what is this? 2 into RC is very much greater than T. Then, can I multiply with pi? If 2RC is very much greater than T, definitely 2 pi also, 2 pi into RC is also very much greater than time T. Right? If you multiply, if 10 is greater than T, then definitely 30 is also greater than T, no doubt. Okay? Therefore, now if I take reciprocal, what is that? 1 by 2 pi RC is very much less than 1 by T. Right? What is 1 by T? Therefore, 1 by T is nothing but the frequency of your input signal. 1 by T is nothing but frequency of your input signal. Then that should be very much greater than 1 by 2 pi RC from frequency domain is nothing but your higher cutoff frequency, where FH is nothing but, where FH is equal to 1 by 2 pi RC. Okay, take it. Therefore, whatever condition we got in the case of frequency domain analysis, where the frequency of your input signal should be very much greater than higher cutoff frequency of your circuit. The same thing we also got from time domain analysis, saying that the time constant of the circuit should be very much greater than the input time period. Then we get slow charging. Slow charging is nothing but linear ramp. Linear ramp is nothing but triangular wave. Therefore, integration of square wave. That is what it is. Okay. Take it. Try to correlate between frequency domain analysis to time domain analysis. Try to use 3 different colors, else it will be confusing. Therefore, the black is charging very fast, blue is okay, and red one is charging very slowly because of time constant of the circuit. Okay, take it. I'll give you 1 more minute. Try to complete in that time. After that, I'll explain what is active integrator using Opamp. Can you continue? Over? Okay. Write down active integrator. Active integrator. With that, integrator is over. If there is a capacitor in the feedback of Opamp, you can consider it as integrator. This is Vi, this is R, this is C. Okay, we have 3 minutes time to complete the session. Right? Let me explain. Then, if time is okay, then fine. Else we can see in the next session. Okay. Now, negative feedback or positive feedback, you treat this as an Opamp problem. The negative feedback or positive feedback, negative feedback, because you are sampling output and then feeding at the negative terminal, right? Provided input is having some frequency, non-zero frequency. Else your capacitor is open. When capacitor is open, remember it is open loop Opamp, then virtual ground concept is not valid, it is nothing but a comparator, right? Now for non-zero signals, non-zero input signals, non-zero frequency input signals, let's see virtual ground concept is valid. If virtual ground concept is valid, right, tell me this is 0, what is the voltage? This is also 0. This is also 0. Then if you do nodal analysis, then let us say this is what is having the voltage across the capacitor is V, C, and the current which is what is flowing through the capacitor is, let us say, IC, right? Then tell me, current leaving from this node, 0 minus Vi divided by R plus current which is what is leaving from this node is nothing but current flowing through the capacitor, which is nothing but C into dVc divided by dt is equal to 0. Okay. Now what is Vc? If you take the capacitor, this is nothing but what, C into dVc divided by dt is equal to Vi divided by R. What is Vc? If you take the capacitor, this is what your capacitor, right? Now this is what is 0 volt and this is what your output voltage. But according to the representation, this is what is plus minus Vc. Therefore, what is Vc? Vc is equal to 0 minus V0, which is nothing but minus V0. Okay, take this. Therefore, let me call this as equation 1. Okay, time is almost over in this session, right? Let's see, you can wait we can continue in the next session, right? We will continue and I'll close the derivation part. Okay, thank you.